Hello, this is Brother Kumar from the Math Department at BYU, Idaho, and these videos will be covering Lesson 12, which is dealing with inference for one mean, sigma unknown, or population standard deviation unknown. And this will be the outline for these videos. First, we'll cover the t-distribution. We'll compare that to the z-distribution, which is what you've seen before. Then we'll discuss one sample mean standard deviation unknown with hypothesis testing. Then we'll discuss it with confidence intervals, and then we'll finish it up with dealing with checking with assumptions. Okay. So first, let's talk about t-distributions and compare it with the z-distribution. So here's a representation of a t-distribution. The t is the curve in red, or it's represented in the curve in red, and the z-distribution is represented in the curve in blue. Now you notice a couple of things with the t-distribution relative to the z-distribution is that the tails on a t-distribution are thicker. Okay, the reason for that is that there's a lot more uncertainty when we're dealing with when we don't know the population standard deviation, and so we have thicker tails on the outside. On top of that, also that there's fewer data at the center compared to a z-distribution. But notice what happens. So what we'll talk about later, what degrees of freedom are, and for this test, it's the sample size -1. So this is an example, say, of the degrees of freedom being 1. But notice what happens as the degrees of freedom, or in turn the sample size, increases. Notice what happens to the curve, the red curve. It's drawing closer and closer to the z-distribution. And so as we increase our sample size, and that t-distribution draws closer and closer to the z-distribution. Okay? So now what I'd like to do is that I'd like to talk about hypothesis testing when it comes to the one mean sigma unknown. Okay, so now let's go back to lesson 9 when we knew the standard deviation. So we state the null and alternative hypotheses. That's the first. This is what we'll be doing with what we're doing in lesson 12. We compute the test statistic. We get the p-value from the applet using our test statistic. We then go from the p-value, we compare the p-value to the level of significance. And if the p-value is less than the level of significance, we reject the null. If not, then we don't reject the null hypothesis. And then we state our conclusions based on what we did on step number 4 in the decision rule. If we reject the null, we have sufficient evidence to say that, and then we state the alternative hypothesis in English. If we don't reject the null, then we have insufficient evidence to say that, and then we state the alternative hypothesis in English. So now what we'll do is that now we'll jump to what we're covering here in lesson 12, which is where we don't know the standard deviation. Okay. Now if you notice here, steps 1 and then 5 and 6 are the same. They're not changing. Okay, it's what we did back in lesson number 9 when we dealt with the one mean standard deviation known is the same with what we're doing with lesson 12 with one mean standard deviation unknown. The items that change are from steps 2 through 4. Okay. Now, for instance, in step number 2, computing the test statistic, here's the formula for the test statistic. However, we'll be using, depending on your class, Excel or SPSS to get the test statistic. The degrees of freedom that's the next step, it's n-1, basically the number in the sample size that you got -1, and that's your degrees of freedom. Okay, and we want that recorded because we want to know, if you remember, the different shapes of the t-distribution they change based on the degrees of freedom. Okay, step number 4 is get the p-value, and we're going to get all 3 of these from output, whether it's Excel or SPSS. And then we go to what you're familiar with step 5 and 6. Okay, so let's go through a couple of examples. Okay, so we want to conduct a hypothesis test to determine if the mean body temperature is different from 98.6 degrees Fahrenheit. And we'll set alpha, I don't say it up here, but we'll set alpha equal to 0.05. So step 1 is state the null and alternative hypotheses. So the null is that the mean is equal to 98.6 degrees. The alternative is that the mean is not equal to 98.6 degrees. We're looking to see if the temperature is different. Okay, so steps 2 and 4, we are going to get it from output. Now I'm just going to show you SPSS output, which will, for you Excel users, it's similar looking to what you would see in Excel. If you have any questions, you can talk to your instructor. But here's an SPSS where you get steps 2 through 4. This is our test statistic here. It's under the T. This is our degrees of freedom, 147, so that means our sample size is 148. And this here is, and I think in Excel it does say p-value, but here in SPSS, This here is a p-value only for a two-sided test. If this were a one-sided test, what we'd have to do is we'd have to take this number and divide it in half. Now in this case, the number is, it says 000. It's not exactly 0 because remember, it's never going to be 0. There's going to be some type of probability, but it's going to be close to 0. Okay, so it's a number that's close to 0 divided by 2. That would be your p-value, and it's still going to be something that's close to 0. So steps 2, 3, and 4, I put this here on my PowerPoint. And the p-value is equal to close to 0. So because the p-value is close to 0 and compare it to our level of significance of 0.05, we would reject the null hypothesis. P-value is low, reject the null. And so therefore, in our conclusions, we say we have sufficient evidence to say that the mean body temperature is different than 98.6 degrees. Okay. So now what I'd like to do is I'd like to go through, I'm going to go past this example, let's go through one more example. Okay. So birth weights of a child is an important indicator of their neonatal health. It's important that pediatric healthcare providers track changes in the birth weight over time. The birth weight of children in Australia has historically had a population mean of 3,373 grams. Is this still the mean birth weight of Australian children, or has there been a decrease? Now, I put that in bold. We would use the level of significance of 0.05. You've seen most of this in the online textbook. I changed one phrase to it. I wanted it, and you'll know why in just a sec here, but I put this in here just to adjust the problem a little bit. So step number 1 is what? It is state the null and alternative hypothesis. So this is how we'd write the null and alternative hypotheses. So now what I want you to do is that stop the video and see if you can do steps 2 through 4 based off the data that the link to it is in the wiki. Okay. Now steps 2 through 4, we would use software, and so what I'm going to do is let me go to the output in SPSS, which is similar looking to Excel as I mentioned before. And this is where we get the test statistic, degrees of freedom, and p-value. This here is our test statistic. This is our degrees of freedom. And now, since we are doing a one-sided test here, this is no longer the p-value. What we have to do is take this number and divide it in half to get our p-value. So in this case, our p-value, what I got here is 0.114 when I do a little bit of rounding, 0.114, or it could be 0.115. Now in this case, our p-value is greater than our level of significance. So therefore, we do not reject the null hypothesis. Okay? So because of that, our conclusion is that now we have insufficient evidence to say that the mean birth weight of Australian children has decreased from 3,373 grams. So this concludes part 1 of the lesson 12 videos, and in part 2, I'll be covering confidence intervals and checking assumptions.